Hey guys, this is lesson 3 for Math 30-2 in counting methods. So this is permutations with distinguishable or distinct objects. Um, so this is really continuing on to what the last lesson actually was. So up at the top there in your notes package, hopefully you still have your cards from last day. So it says from a deck of 52 cards, choose 3 different cards, and to make it easier, make sure they're all different suits and different numbers. So using these 4 cards, fill in the chart for how many different ways there are to arrange only 2 of them at one time. So only taking 2 of the 4 cards, how many different ways are there to arrange them? So I want you to give that a try now. So choose 4 different cards. Oops, I don't have my pen on. So pause the video because I'm not just going to sit here in silence. Pause the video and try to arrange the 2 different cards. So I'll just write out the ones that I picked. So the 4 of hearts, the 3 of diamonds, the 2 of clubs, and the ace of spades, all really easy to tell apart. If you're choosing the same number, you might mix something up, or if you're choosing the same suit, who knows, something funky could happen. So I could, in arrangement 1, pick my 4 and my ace. Or arrangement 2, I could keep my 4 in the first position and now have the 2 there. Keep my 4 in the first position, have the 3. Oh, I can't do that. We gotta change this to a 1 with a weird cloud in front of it. So if I put my ace in the first position, now I could have my 2 in the second position. If I put my ace in the first position, I could have my 3 in the second position. My ace could have my 4. If I put my 2 in the first position, could have my ace in the second position. If I put my 2 in the first position, have my 3. So it kind of gave you a hint that there might be 12 arrangements. If you try to add another one, whatever you put in these 2 spots is probably somewhere else here. So there are 12 different ways to arrange 2 cards, choosing 2 of the 4 possible cards. So in total, we found 12 possible arrangements. Oh, not 12 factorial. Don't write an exclamation mark. Did any of the groups find more possible arrangements? I hope not. Do you think it would make a difference if some of the cards were the same? Again, it could be hard to tell the difference for some arrangements. So how is this question different than the questions we answered last class? So looking at the ones last class, we had students lining up for lunch. We had arrangements of people's names using all the letters. So this one's different in that we did not use all of our objects. And so in this case, the objects was the cards. So we had 4 possible cards to choose from, but in each of the arrangements, we were only arranging 2 of the cards. Does factorial notation give us the correct answer? So if we were to go for factorial, because we have 4 cards, we get 24, which, nope, not the right answer, because 24 is not equal to 12. So factorial notation doesn't work when we have this situation, when we're not using all of the objects. We have a little bit of a different equation, I guess you could call it, that still involves factorial notation, but just using 4 factorial does not give us the right answer. Oh, sorry. So when we found the number of possible distinct arrangements of cards, this is called finding a permutation. Again, when we're talking about permutation, order matters. You saw that we had an arrangement with 4 and A, so an arrangement with 4 in the first position and A in the second position. That's different than A in the first position and 4 in the second position. So that's a different arrangement. So these are different arrangements because orders matters. Because again, if you're lining up for something, if you're being arranged, where you're standing in line could matter. You could get into the movie, or you could get on to the next roller coaster or whatever if you're closer to the front of the line. So order matters when we're talking about lining things up or arranging things in a permutation. This is notice that we did not select all possible cards for each different arrangement, but this is still a permutation. So in general, for permutations when not all objects are selected, of course, that definitely came down too low, is calculated as, so this is called our permutation notation. So permutation notation, what we see is there's like a little subscript n, then there's a big P, and there's a little subscript r. So this is saying n is the total number of objects. I probably want the word number there. So the total number of objects, and R is the number of selected objects, or how many are we arranging. So you're never going to have your R number be greater than N. So we can't say there's 6 cards. How can you arrange 8 of them at a time? Well, you can't because you only have 6. So your N number is always going to be greater than your R number. And again, this P indicates we're talking about a permutation where order matters. We'll talk about combinations a little bit later, but we're really going to focus on permutations still for a couple more days. So our general form in the equation is n factorial, so whatever our total number of objects is, divided by n minus r factorial. So the way that, actually I'll do the calculator strokes in a bit. So you could always punch in this formula. So for our cards example above, we had 4 factorial divided by 4 minus 2 factorial. So 4 factorial, again, we know is 4 times 3 times 2 times 1, which is 24. 4 minus 2 factorial is just 2 factorial, which is 2. So that gets us 12, which we had. We had 12 possible arrangements. The way to put this into your calculator, again, Jax, I still don't have the Casio in front of me, but I think it's pretty easy to find. So you might either be in statistics, or if there's in the main menu, if there's something called probability or statistics, I would think it's going to be under probability. But again, if you can't find it, just message me right away and I'll figure it out with Mademoiselle Corey. So in the TIs though, you would type in whatever your n value is. So whatever your n value is, and then you press math, and then you scroll over again to PRB, and then it's number 2, which I'll have to look at my calculator, which says n NPR, and then you put in, once you press enter, and then you put in whatever your R value is. So I would say practice that right now to make sure you can put it into your calculator. So with the last question, you would put in 4, then you would do this step, sorry, and that'll get you NPR here, and then you would put in your R value, which again, your R value is the number of selected objects, so we're selecting 2 at a time. So your calculator should look something like this. 4, and then the letters NPR, and then 2. And so once you calculate that out, once you press enter, you will get 12 arrangements. I'm trying to think, Jax, I'm thinking there's something a little bit funky with this. So again, please email me as soon as you can if there's something funky, and I'll see if I can figure it out with Corey quick, or if I can do a quick internet search for what it would be. But again, you're a calculator whiz, so you might have it. So it says, often we will prefer to write our permutations using factorial notation. Or the fundamental counting principle methods from the last lesson instead of using permutation notation. So usually permutation questions, there are multiple ways to get to the right answer, whether you're using the fundamental counting principle or using your permutation notation and factorial notation. So know that quite often there are more than one way to get to it. So that's the end of the lesson. What I would really prefer is you do the questions now. I think I have 2 of the questions in here that I just want to go over just to make sure kind of the explanation makes sense for it. So do what you can from the next 6 questions, pause the video, and then come back to it. I want you to have attempted the questions before though, so give it a try and come back. So hopefully you've now done all the questions. I'm just going to go over question 2 and question 4 with you. So question 2 says, Nick has downloaded 12 of his favorite songs from a completely legal website. Nobody believes that. How many different 6-song playlists can be created? So maybe Nick's bus ride is about as long as 6 songs, or he likes to go for a run that's 6 songs long. So how many playlists can he get from these 12 songs that he has? And so again, when we get to combinations, you need to ask yourself, does order matter? And so in this case, order could matter. So if we're talking about him going for a run, maybe he needs his kind of hype up song first to get going, and then he wants to finish with his absolute favorite all-time song. So order does actually matter when you're creating a playlist. We'll talk about when order doesn't matter, and that's in your combinations, but order does matter. So we have a permutation. So how many different 6-song playlists can be created? So again, we have 12 possible songs, and we want to make a playlist from 6 of them. So we have 12 objects, which are our songs, and we're choosing how many different ways can we arrange 6 of the 12 songs. So we can put that in our calculator. So again, put it in, do math, scroll over to probability, and I think it's number 2. So 12 NPR 6. And so what you would get there is 665,280. So you could put it in that way. That's one way you can do it. You can do it as that equation that we have on the back side, where if we're talking about a permutation of 6 objects out of 12, it's equal to n factorial divided by n minus r factorial. And so that would be, so n factorial is 12 factorial. And on the bottom, it's 12 minus 6 factorial. So again, you can punch that into your calculator and lo and behold, you'll get to the same number. The other way that we could do it, just to kind of talk about this, is we could do the fundamental counting principle. So this is, the first two ways is using more of a permutation idea, but we could also think about our fundamental counting principle. So he wants a 6-song playlist. 4, 5, 6. So how many songs could be in the first position? Thinking about it, how many songs could be in the first place? You guys are all right, you're so smart. 12 songs could be in the first place, right? He has 12 songs to pick from. Now he doesn't want to repeat, that's no fun in a playlist. So he could have 11 songs in the second position, then 10, then 9, then 8, then 7. So we could punch all of those into your calculator. 10 times 9 times 8 times 7. What did I say there? 12, 11, 10, 9, 8, 7. I don't think that's what I said. And so when you would do that, you would get to the same answer. So this is what I meant before when I said you can use fundamental counting principle or more the idea of permutations, but it's doing the exact same thing in the end. So now question 4, at a car lot, 7 different car models. 3 of them are red, 4 of them are black, are parked in a row, but again, they're different cars. So even though it says there are 3 red cars, one's a minivan, one's a truck, and one's a little compact car, so you can tell them apart. Yes, they're red. And your black cars, again, they're all black, but one's a car, one's a truck, one's a Jeep, and one's a stretch limousine. Weird. So they'll to be parked in a row. So how many different ways can the cars be parked? If the row of cars must have a red car at the start, the middle, and the end of the row. So this one you can't really use your permutation notation because it's giving you some restrictions. So in this case, we have some restrictions on how things can be organized. So I'm going to use my fundamental counting principle. So 1, 2, 3, 4, 5, 6, 7. So it says there needs to be a red car at the start, in the middle, and at the end of the road. So this means that this one needs to be a black, a black, a black, and a black. So it's saying how many ways can these cars be arranged if this needs to be happening. So I guess it maybe looks nice. I don't know why. So how many cars can be in the first position? So looking back, there are 3 red cars. So if it has to be a red car, it needs to be one of the 3. It doesn't matter what order you're going to do this in. So I'm going to do all my red cars first. So we already have 1 red car in the first position. So for the middle, now we can only have 2 cars that can possibly be there. And in our last position, it needs to be whatever our red car is that's left over. So our second position, again, needs to be one of the 4 black cars. So there are 4 possible cars that can be there. 3 that can be in this third position. 2 that can be in this position, and 1 that can be in this position. So it's going to be 3 times 4 times 3 times 2 times 2 times 1 times 1. You don't need to do the times 1s if you don't want. And so that gets us 144. There is kind of a way, if you looked at my notes, there's a way that you can think about it in terms of factorial notation and permutations, but I kind of like to use the fundamental counting principle here instead. So it says, the next one says, the 3 red cars must all be parked in the start of the row. So 1, 2, 3, 4, 5, 6, 7. So we know the first 3 need to be red cars. The last 4 need to be black cars. So how many can be in the first position? 3, 2 in the second position, whatever's left over in the third, Now to the blacks. 4, 3, 2, 1. So again, we get 144. Because we actually have the same type of restrictions. So we have particular places that my red cars need to be versus black cars. So what that actually looks at in terms of factorial notation is we're organizing our 3 red cars in a particular way and our 3 black cars in a particular way. Here we had the red cards arranged in the first, middle, and last position. Here we had our reds in the first 3 positions and the blacks in the second 3 positions. We're getting to the same answer though. The next one though is why I wanted to do this one, because as it says, it's a little bit of a tricky one. So it says the 3 red cars must all be parked together. So I'm going to give you a little bit of an idea what this represents. So let's go 1, 2, 3, 4, 5, 6, 7. And then what I'm going to do, sorry, I did it in a way in my, I'm going to say that just to start, those are my red cars. So this is black, 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 black. So if those were my red cars, 3, 2, 1, black, 4, 3, 2, 1. So we know that that's going to get me that 144 again. But now, so we have my 3 red cars together. I'm going to make my life a little easier. So we have our 3 red cars together right now. We have them in positions 2 through, so 2, 3, and 4. We could also, though, move the red cars to positions 1 through 3. So we could have the 3 red cars right here. We could also move the red cars down 1, so we could have it in position 3, 4, and 5. We could have it in position 4, 5, and 6. Or we could have it in position 5, 6, and 7, so at the end. So there are in total 1, 2, 3, 4, 5 different places where the 3 red cars can be. So we would actually need to take that 144 and multiply it by 5 in order to figure out where the red cars would be within the line. We know they need to be together, but we would need to figure out where they actually are. The other way that we can look at that is if we just kind of think about organizing our black cars first. So again, our 4 black cars, 1, 2, 3, 4, and again, 4 times 3 times 2 times 1. So that's organizing our black car. So 4 times 3 times 2 times 1 is 24. I'm sure there's an easier way than just escaping out of this, and I'm sure you would be able to tell me if you were in front of me. Then we can think about arranging our red cars. So 3 times 2 times 1. So we know they're going to be all together, but they can be in any order altogether. So 3 times 2 times 1 is 6. And now we need to look at where our arrangement can fit. So we can put our arrangement of our 3 red cars first. We can put it second. We can put it third. We can put it fourth. Or we can put it in the last position. So there are 5 places where these 3 red cars can fit within the arrangement of black cars. So we would have to go 24 times 6 times 5 still gets us 720. So that's that tricky one. You'll see something like that on one of the assignments I remember, so think about that as you go. All right, that's it. That's all. Good luck with the questions. And that's it kind of for this week. So make sure you do all the questions in the booklet and then have a peek at my key. Okay, bye guys.